All right, how's it going, everybody? I am here making this video on Tuesday, April 27th here, and today we're going to be talking sections 11.6 and 11.7. We're going to talk about absolute convergence, we're going to talk about the ratio and the root tests, and we're going to talk a bit, more broadly about strategies for testing series. So we're going to look at a couple series where we're going to kind of walk down our list of possible tests that we might want to throw at it right here. And that's in general, I think, a good strategy for us to have. And that's kind of what we're going to start with right now is a little bit of a summary right here is that you should just have in your back pocket here just a list of all of the tests that you might want to throw at a series so that you can judge whether it is convergent or divergent. It's certainly the case that you should have some intuition about which tests are going to be the most reasonable to apply in any given situation. But it's also the case that it might be the case that you're going to try 1, 2, 3, 4, 5 things that don't work. And then on the sixth test, you're going to finally get some result that you've been looking for out there. So it matters that you have sort of just like a checklist of things that you can check off. So let's go ahead and look and see at the things that we've already seen. Let's use that list to determine what are the types of series that we haven't yet discussed based on seeing what we have discussed. And then today we'll get some new tests that will help us kind of wrap up those remaining situations there to the best that we can right now. So summarizing what we've seen so far. So I think that one of our easiest series for us to talk about are geometric series. The reason why these are the easiest to talk about is because if we can find that a series can be written in this form, we automatically will know if the series converges or diverges just by looking at the size of one number, right? This is like our easiest test in a sense right here for geometric series. The other thing that's extra good about geometric series is that if it converges, we guarantee that we know exactly what it converges to. That's like rare, that's like doubly rare, right? Like none of our series have this simple of a test. Is one of your numbers less than 1? And if they do, no other series gives us a known convergence value like this, right? So geometric series are really the type of series that we for sure know the most about. All right. But also not exactly, well, yeah, we know the most about geometric series. We can't say as strong as statements about any other series. The next test that we got was our test for divergence back in section 11.2. And we said that if a series is going to be convergent, then that guarantees that the individual terms are eventually getting infinitely small as the index gets large, right? As our index n gets infinitely large, the size of the terms get infinitely small. If it is the case that the size of the terms, if we take that limit as n goes to infinity to look at the size of each individual term, if that limit doesn't exist, or if that limit's not equal to 0, then the series is divergent. And that kind of makes sense to me because this says if our terms aren't getting infinitely small, then that means that we're still making like a meaningful contribution to the size of the sum with every single term that we have. That's going to guarantee that sum is going to blow up in value over time. We need all the terms to be eventually trivially small so that our sum does not get infinitely large to diverge. Right? The next thing we saw was the integral test, and we want to remember that the integral test required that we have all positive terms, and it required that we're able to state some function f of n that is equivalent to the expression of the terms a sub n, right? The descriptor of the nth term a sub n must be able to be written in function form for us to use the integral test, because the integral test says we're going to take the integral of that function, right? So if the integral is going to be convergent or divergent, then we'll have the equivalent convergence or divergence associated with the equivalent series partner right here. You should definitely be remembering for the integral test, you should be visualizing that Desmos page that we spent a good chunk of time on that day. Remembering that when you're visualizing what the integral test is doing, it's basically like our Riemann sums, right? Saying that that's how we know that the size of a sum can be greater than or less than the size of an integral. And ultimately, the integral test is really like a special case of the comparison test. It's just not comparing two equal things, right? It's not a sequence and a sequence, a series and a series, or an integral and an integral. But the integral test did do a comparison between the amount of area underneath a curve and the area underneath a bunch of rectangles with width 1. So this was sort of like a special case of the comparison test with the integral test here. Then we saw p-series. P-series are another thing that kind of go with the geometric series of being one of our easiest tests to apply if it applies, because we just straight up have to ask ourselves, is a number more than 1 or is it less than or equal to 1? We saw that if the power in all series of the form 1 over n to the p power, we will converge if the power is larger than 1. We will diverge if the power is less than or equal to 1. And you should all just briefly remember that if that p is equal to 1, that's the series 1 over n. That is the harmonic series. And that's, as we have seen in all of our videos, it's one of our most common comparisons that we make is to the harmonic. Then we saw our comparison test for series, which, by the way, this is the third comparison test that we've seen this semester. We want to remember again that the comparison test requires all positive terms. And I think that we know the comparison test by now because this is the third time we've seen it. But it says if the series that we are interested in it can be shown to have all terms that are individually all less than the terms in another known convergent series, then our series also converges because all of the terms of our series were all underneath the terms of a known convergent series. So we were less than a convergent series must also be convergent. Alternatively, if every one of the individual terms in our series is known to be larger than the comparative term in a known divergent series, then all of our terms are bigger than the terms that result in divergence. Therefore, our given series of consideration is also going to diverge. So smaller than a convergent thing or bigger than a divergent thing are the two cases where we can use the comparison test to establish convergence or divergence. Obviously, there's two cases that result in no conclusion. If our series is below a divergent series, we don't know if it's smaller enough to converge. If our series is above a known convergent series, then we don't know if it's bigger enough to diverge, right? So out of the four possible comparisons that are possible with that greater than, less than right there, two out of the four result in us being able to establish convergence. Divergence, two out of the four give us no information. Then we said, well, sometimes the comparison test fails us for making direct comparisons between the individual terms. However, the limit comparison test says to us you can take the ratio of the two terms. And remember that what we said about this was that if we end up finding that the limit of the ratio of the equivalent index terms from the two different series is equal to some constant c eventually, then what that says is that eventually the terms in one series are just a constant multiple c of the other series. And therefore, if that series converged, then the other series just converges to c times that amount. And if that other series diverged, then our series is c times as much as a divergent series, so it also diverges. So this is essentially, I interpret this to be sort of like a roundabout way of saying a constant multiple of a series is going to share the same convergence divergence behavior of the non-constant multiple of the series. The only thing that we're saying here is when I say the constant multiple of the series, that literally means take like c times the entire series. In this case right here, what we're saying based on this limit statement here is it might not be the case that every single a sub n is equal to c times b sub n, but they need to eventually be constant multiples of one another. So it's not quite just saying one series is a constant multiple of the other series. It's saying eventually, as n goes off to infinity, the terms of one series eventually look like the constant multiple of the terms of the other series. Then they should share the same convergence divergence behavior. Our alternating series test, then, for our alternating series, where we have alternating sign every single term, right? So notice, by the way, I'm going to scroll back up real quick. And let's see here. We got requires all positive terms, requires all positive terms, requires all positive terms, requires alternating sign every term, right? So for alternating series of this form, if it is the case that our terms are always decreasing or at least equal to one another, and if our terms are eventually getting to be zero in size, then the series will converge. This makes sense to me because of the nature of the alternating series, the positives and the negatives. We know that they're going to experience, in a sense, a little bit of cancellation, right? The negative terms are going to cancel out a little bit of the previous positive term. Since every term in magnitude is getting smaller than the previous term in magnitude, and since they are condensing on zero, what I know is that the largest possible value of this series is literally its very first positive term, b1, or its very first negative term if we're going to get a negative value for the series out there as well. So there's guarantee that each term in the series is going to be less than or equal to the previous, and that they are eventually tending towards zero. It says to me, again, that the largest value that this series could ever take on is b sub 1. That's the biggest it could ever be. And if the biggest it could ever be is a number b sub 1, then it is bounded below. If the first term is positive and the next term that's negative is smaller than it, then it's also guaranteed that it remains positive, so it's greater than zero. So this now then sounds to me like an alternate version of that monotonic bounded theorem that we saw. All right, so far, every rule requires that we have either all positive terms or terms that alternate sign every term. Further, we can note that the tests that require all positive terms also cover scenarios with all negative terms, because we could just factor out that negative to be out sitting out front of the sum, and then the sum would contain just all positive terms, right? So it seems like we've handled all positive terms, all negative terms, alternating positive and negative terms. And so it seems like the series that we still are interested in discussing are series that have both positive and negative terms, but that don't necessarily alternate every term. So our issue now is going to be that we've got, some spread of positives, some spread of negatives that are out there. And so what we're going to do to help ourselves discuss this is we're going to talk about throwing our terms inside of absolute values here and see if we can make some meaningful statements about this. So in general, here's our definition for us. We say that a series is absolutely convergent, not just convergent, but convergent in absolute value if you take the sum of all of the absolute values of all those terms. That's like saying let's just ignore the fact that any of those terms were negative, and let's just consider them all to be all positive terms out there. We're not getting convergence, but we would be able to establish a thing that we are calling absolute convergence. So new definition right here. This isn't really like a theorem stating anything. This is just a thing we're defining right here. So notice that in this case right here, we can go ahead and consider the absolute value of this series right here. Let's just say that. Let's consider. So when I take the absolute value of this, what you should notice is that the absolute value just says discard all the negatives. Well, all the negative components are coming from the -1 to the n plus 1 power. So this would be just equal to the series 1 over n squared. And we know this converges. How do I know it converges? It's a p series with p equal to, and that is greater than 1, so therefore it converges. And therefore, I feel already comfortable saying the series -1 to the n plus 1 times 1 over n squared is absolutely convergent. Right? It converged when we took the absolute value of every single one of the terms there, right? The absolute value essentially caused us to ignore the -1 to the n plus 1. This term does not affect any magnitudes. It only affects positives, negatives. And absolute value says just make every term positive right there. Now the next question is, does it just straight up converge? We saw that it is absolutely convergent. I don't know if it is just regular old convergent. So let's say it is in the form associated with the alternating series test. So we've got two checks that we want to consider here. My first question is b sub n plus 1 less than or equal to b sub n? In this case, we would see 1 over n plus 1 squared. We're asking, is that less than or equal to 1 over n squared? And I'm going to say, yes, that is true for all n greater than or equal to 1 right there. That's a clearly true statement. We clearly have larger denominators, therefore this is smaller overall. We also want to check, that was check number 1. Check number 2, is it the case for the alternating series test that our terms are eventually going to 0? And in this case, I can see that, oh my gosh, same problem as last video. I cannot stop myself with this limit. I'm just going to write a b down there every single time, apparently, for my whole life. Oh my gosh, b is not going... n is going to infinity. That's the limit that I'm taking every time. I don't know why I can't write this. Okay, limit as n goes to infinity of the b sub n's, that's the 1 over n squared. That's clearly going to 0. And so it looks like by the AST, this series is also convergent. So it seems like what we just found about this guy right here is that we checked the absolute value of each of the terms and saw that that represented a p-series, and therefore that series converged, but that was the absolute value of each term. So we would say that this is absolutely convergent. And by use of the alternating series test, we found that it was also convergent. It was a convergent series. It converged, right? So it was both absolutely convergent and convergent. We want to kind of make a conclusion here after we look at our second example about what that's going to mean to us. Now, for our second example here, you can see that what we've got is what we refer to as the alternating harmonic series here. It's the harmonic series, those 1 over n's, but we're going to make every other term be a negative. So first, let's check for absolute convergence. And in this case here, we would check out the sum of the absolute values of the terms. In this case, that would just give us the harmonic series, right? That would just give us 1 over n for our terms in our series. And I know that this diverges because it's a p-series with p equals 1. And so therefore, the series is not absolutely convergent. But what about regular convergence? Well, I'm noticing that this is in the perfect format for the alternating series test right there, so I'm going to go ahead and check that guy out. What we can see here is that our b sub n plus 1, we want to check 1, is the b sub n plus 1 less than or equal to b sub n? Well, that's just 1 over n plus 1 being less than or equal to 1 over n. That's going to be true for n greater than or equal to 1, so I'm good with that. Second, we want to check, is it the case that the limit as n goes to infinity of b sub n, is that going to be equal to 0? In this case, the limit as n goes to infinity, I'm so proud of myself right now, of 1 over n is clearly equal to 0. So it seems like, getting ahead of myself right there, that by the AST, alternating series test, the series negative 1 to the n plus 1 times 1 over n is convergent. So it seems like the harmonic series is our classic example of a series that does not converge. It's a divergent series, but it seems like the alternating harmonic series does converge, which is interesting right there. So we got here for this one, it's not absolutely convergent, but that it was convergent. All right, so in our two examples here, our first example was both absolutely convergent and convergent. Our second one didn't converge absolutely, but it did converge when we did include the negatives. And here's kind of the thing that I'm thinking now. Absolute convergence should be sort of harder to achieve. And the reason why is because if there are some negatives mixed in with your positives, then you're experiencing a bunch of like cancellation of value, right? We're not necessarily getting just bigger with every single term. If we converge absolutely, then that means that even if you took the positive version of every term and accumulated all those magnitudes, if even that is going to be a convergent value, then if you were to also include some negatives by just looking at regular old convergence, it certainly seems to be the case that that should also then converge because the value should plausibly be smaller, or in its most extreme should just be the negative version of the same series that you already had shown converged. So one of the things, so again, I'm going to repeat what I just said there. It seems like absolute convergence should be harder to achieve because it's the version where every single term is positive. You don't get the luxury of some negative terms kind of reducing the value of your series, preventing it from diverging. So it seems to me like absolute convergence is difficult to achieve because it guarantees that you're adding up all positive terms. Regular old convergence, when you have some positives, some negative terms, seems a bit more likely because you've got some of those negatives canceling away some of that positive value that you're accruing out there. So conditional convergence is when we do converge, but when we don't converge in absolute value. And we are going to see at the end of this video that some really weird things can happen when a series is conditionally convergent. When it does converge, like this guy right here. In fact, we're going to look at exactly this series again at the end, and we're going to see some very strange stuff is going to happen with this series here. So notice that this series did converge, but then when we took the absolute value of all of its terms, it no longer converged. All right, so that's referred to as conditional convergence. It converged, but when we took the absolute values, that made everything a bit too big, and it then diverged. And I promise when I say really weird, I'm into weird stuff. This is like way up there on the weird list. All right. So here's our important theorem that's describing what we were just sort of summarizing what we saw up above there. If a series is absolutely convergent, if it converges even if you took the positive version of every single number, then it seems reasonable to me that it should just be regular old convergent, and we're going to write a proof of it right here. But again, my argument here is that if you were to take every number's positive version and even that converged, then if you switched some of the positives to negatives, then you should be getting a smaller overall value for your series. And the most extreme that this could go is if you turned all the positives to negatives, you're going to get the exact same magnitude just on the other side of zero on the number line. And if all of it converged to the positives, then it's going to converge to the same value in the negatives in its most extreme case. So it seems completely reasonable to me to say that if a series converges with all absolute values around each individual term, that's like the most positive stuff that you could ever get. The regular old convergence includes some negatives, so it should be smaller. So you should notice that I'm making some sort of comparison here between the series with all positive terms and the series with some positive, some negative terms. So it seems like a comparison test might be a good way to prove this in general, and that is in fact the way that the book goes ahead and proves this. So the argument that the book sets up, or I should say the book does a smart thing of setting up a good inequality that's associated with this, and so here's their argument. Let's suppose that this series, defined by the a sub n's, is absolutely convergent, meaning that if we took the absolute value of each individual term in the series, then that series in absolute value will converge. And importantly, so we're thinking of the absolute value being on each individual term, right? So the point then is if this series converges, then it should certainly be the case that 2 times that series converges, because whatever finite number this series is equal to, you could just multiply that number by 2. It is never going to be the case that multiplying by 2 a single time is going to push you over the threshold from convergent to divergent, right? You're just getting 2 times whatever the previous number was. We can use this fact in association with the comparison test to arrive at the desired result, and so let's consider this inequality. In this inequality, what we're seeing here is that 2 times the absolute value of the a sub n's is the upper bound for the sum of the original series and the absolute value of the series. And let's think about this again in terms of the extremes. Here's the 2 extremes that could happen. The first extreme I'd like you to consider is all of the a sub n's already being positive, right? So that the absolute value didn't do anything. If all the a sub n's were already positive, then this sum in the middle right there is equal to 2 times a sub n. And so therefore it is equal to the upper bound of our compound inequality, 2 times a sub n. On the other hand, if you consider the opposite extreme where all of the a sub n's were actually negative originally before we took their absolute value, then it should be the case that if you take all of the a sub n's here, the negative version, and all the a sub n's here, the positive version, then in the other extreme, this sum right here should be 0 because we're taking the negative and the positive of the same number and adding them together, and that would therefore give us our lower bound on this inequality. So our 2 kind of extreme cases to consider here is if all the a sub n's are positive and if all the a sub n's are negative, that clearly gives us the bounds on this compound inequality, and therefore if there's a mixture of positives and negatives in there, it should certainly leave us sitting in between 0 and 2 times the absolute value of a sub n. All right. So one thing that we're seeing, so our important thing that we're seeing here is kind of we've justified this inequality, right? So if it is then the case, so now we agree with this inequality. That's where we're at. Now, remember that up above we said that we're assuming this to be a convergent series. We're absolutely convergent, and therefore 2 times an absolutely convergent series should also be convergent. So we are all currently in agreement that this is representative of the terms of an absolutely convergent series. You should notice that these terms are guaranteed to be greater than or equal to these terms. And since this converged absolutely and is larger than all of these terms, therefore a series of a sub n plus the absolute value of a sub n must also be convergent. So our big important thing here is that since this was absolutely convergent by the comparison test, or excuse me, since the terms in absolute value are just convergent, therefore the series with these as its terms is also convergent. And so you should notice that if we therefore then took this convergent series and we subtracted off the other known convergent series of the absolute values of the a sub n's, all we're left with is this series of just the regular old a sub n's, and therefore it must also converge because all we did was the subtraction of two convergent series, right? That just said we literally took one known finite number minus another known finite number. It's guaranteed that we're going to get a known finite number back right there. So the difference of two convergent series is going to have to be convergent there, right? So we built this inequality. We convinced ourselves that it was true. We recognized that these two parts of the inequality represent a perfect setup for a comparison test because we know that the upper bound converges, therefore the lesser part must also converge. Since this is the sum of a convergent component and something else, this must guaranteed be a convergent component. Otherwise, this could have been a divergent series that we're representing within the terms in the middle right there. All right. So this is just our proof of this statement saying, remember, absolute convergence is difficult to achieve. If you've got absolute convergence, that guarantees that you've just got regular convergence, which is really the thing that we're more often interested in discussing out there. So absolute convergence is a stronger type of convergence than regular convergence here. That's your thing to remember. Absolute convergence is more difficult. So if you can reach that threshold, then you have reached the lesser threshold of regular convergence along the way. So here are some examples of series where we can more easily establish their convergence or divergence by finding that they are absolutely convergent rather than showing that they are regular convergent. So even though this is a stronger requirement, a more difficult to achieve threshold, sometimes it's easier to show absolute convergence than it is to show convergence. Just because it's difficult for a series to have this property, that doesn't tie to the fact that it's difficult for you to prove that it has that property. Those aren't necessarily the same thing right there, right? Difficult to achieve versus difficult to prove, not necessarily related right there. So even though it's harder for a series to be absolutely convergent, it's often the case that it's easier to show that something is absolutely convergent. And if you can prove something's absolutely convergent, then you have by default proven that it converges. And that's what we're looking to show in all these cases anyway. So let's go ahead and take a look at some quick examples right here. So this first one right here is clearly an alternating series right here. So it is an alternating series. And so I want to say, sorry, I'm trying to like set up like my thoughts right here, not just kind of plow through writing the proof. This is an alternating series, so we could try the AST. But if it converges absolutely, that would be easier to show. So what I want to consider is consider the series with absolute values. Well, as we've seen, taking the absolute value essentially just says discard the term associated with the negative 1 to the n plus 1 because all it does is flip our signs around. So this is really just 1 over n cubed, which converges. I know it converges because it's a p-series with p equal 3. Therefore, the series negative 1 to the n plus 1 over n cubed is absolutely convergent because the absolute value of it converged. Therefore, the series negative 1 to the n plus 1 over n cubed is convergent. Right. So notice here it was and I'm certain that we could have shown this by the alternating series test, that the alternating series test would have worked right here for sure. That just requires me to do like two checks that might end up requiring math. Instead, I just took an absolute value, recognized that led me to a p series. Therefore, since the absolute value of the terms resulted in a convergent p series, it must be that our original series was absolutely convergent. Since absolutely convergent is a stronger is a more difficult threshold to reach, it therefore implies that we must have also just been regular old convergent as well, right there. So this is a convergent series because it is an absolutely convergent series. And again, the alternating series test would have worked. I just think this is probably the easiest way to show that this is true. So as our next example here, let's go ahead and look at let's get this guy down there. I'll need you up here. The cosine of n over n squared here. So I'm thinking to myself here, let's see. So I'm thinking to myself, this not an alternating series form, right? But cosine of n does take on positive and negative values. And you should notice that regardless of whether you're interpreting n to be a term in radians or degrees, we are not going to get consistent positive, negative, positive, negative, positive, negative here. We're going to get a bunch of positives and then a bunch of negatives and then a bunch of positives and then a bunch of negatives, right? So it's not an alternating series form, but we do take on positive and negative values here. So let's consider the series where we're taking the absolute value of this stuff right here. Now, what I know is this. What I know is that cosine of n is sometimes positive and sometimes negative, but it never is more extreme than the value of 1, right? So I'm thinking to myself, the absolute value of cosine of n is somewhere between 0 and 1, always. So what I know is that this is guaranteed then to be less than the series just 1 over n squared. And the series 1 over n squared converges because of a p series. Which implies to me that the series absolute value of cosine of n over n squared converges by the comparison test. Right? So we're recognizing here that cosine is at most 1. So it must be the case that the absolute value of cosine is less than, I should say, or equal to 1 in all cases right there, right? Or rather, I'm going to get rid of that or equal to right there because the series overall is guaranteed to be less than, because at least one of these cosine terms is going to be less than 1. That's for sure true. So since our series of interest, our absolute value series of interest is less than a known convergent series, this series must be convergent. But again, notice, this is not the series in question. This is the one where we flopped in the absolute value bars. We're still interested in the original. But we've shown by the comparison test that the absolute value series converges, and therefore I can certainly say that the series cosine of n over n squared is absolutely convergent. And therefore, I can say that the series is just convergent, because it's hard to be absolutely convergent. If you're absolutely convergent, you're definitely regular old convergent. If we converged even when we took only when we considered all the numbers coming out of cosine to be positive, then it better be the case that we should experience. And I mean, honestly, think about this also. Like the cosine is going to have like probably like repeating terms out there, right? The same positives as we're going to get from the negatives. I mean, I honestly expect this to do a whole lot of canceling out. I don't think it's going to perfectly cancel out all over the place. But man, I certainly would expect this series to have a value very close to 0 right there. I'd expect there to be lots of positive negative cancellation occurring from that cosine of n term up in the numerator up there. Seems reasonable for me to conclude that right there. So again, in any of these cases where you recognize, and I think, so by the way, I want to come back here and say, this one right here, it does not yell at me, think absolute convergence. This one is yelling at me, try the alternating series test, because it's in perfect alternating sign format right there. This guy right here is not an alternating sign format, but it does have some positives and some negatives. This one is yelling at me, check for absolute convergence right here, because it perfectly fits that mold of it does have positives, it does have negatives, they don't alternate every single term. That's our prime scenario right there to consider absolute convergence rather than thinking about other possible tests that we might use, right? So these are two samples of when you could check for absolute convergence. I think it's the easiest way to do this one, but it's definitely not the only way. Here's one where I think this is by far the best way to do this. It's really set up specifically for absolute convergence discussion because we don't perfectly alternate sign every term. So the absolute convergence theorem then helps us justify two more tests for convergence. They're called the ratio test and the root test. So we are getting two more tests right now. The good news is that they are phrased identically. The structure of these tests is identical. The little computation that we're going to do to check some things is going to be a little bit different, but the structure of the test is going to be identical. So I'll show you what I mean right here. So we've got the ratio test and we've got the root test. The ratio test is going to say to us, for a series of the form, the series a sub n, and notice, we're not like giving any restrictions on positives or negatives or anything like that. What we're going to have is that if the limit as n goes to infinity of the absolute value of the ratio of two successive terms, where the second term is on top and the current term is on bottom, is less than 1, then you should notice that that really kind of means that our terms are decreasing in size in absolute value, right? If the next term is the numerator, but overall the fraction is less than 1, the numerator has to be less than the denominator. So this is sort of one way that we say decreasing, but it's a little bit different than just saying a sub n plus 1 is less than a sub 1, then is less than a sub n, because of these absolute value bars. These absolute value bars are saying I'm only considering the magnitudes of those two numbers. I don't care if one of these is negative, the other is negative, both of them are negative. We're not worrying about those negatives. We're just saying, is the magnitude decreasing from one number to the next all the time? If that's the case, then we are going to be able to say that the series is absolutely convergent, and we know that that implies convergent, right? On the other hand, if the terms of our series are growing in magnitude over time, that's what this inequality is saying right here. Or if that limit goes off to infinity, right? They're getting infinitely larger than one another, right? I like to think about this as them doing one of these things here. We're swinging back and forth, maybe positive and negative, bigger and bigger and bigger in magnitude every term. Then we're going to have a divergent series. Unfortunately, our difficulty with the ratio test is if you take this ratio and if our terms are eventually approximately the same size as one another, the ratio test is going to be inconclusive. And that kind of makes sense to me because it could be that we're just doing plus 100 minus 100 plus 100 minus 100 and we're never actually changing value in our series right there. And so therefore it may be converged before that. But that's not necessarily always going to be the case there. So our ratio test is inconclusive if this limit is equal to 1. So the cool thing about the ratio test is that this limit that we're setting up right here, it's always the same structure. And you just want to know, is it less than 1, equal to 1, or greater than 1 to get absolute convergence, no information, or divergence. This test is really helpful when we can algebraically simplify the ratio of successive terms of a series. So what you should be thinking is it would be really convenient for us to not have lots of addition and subtraction in our series description and to have lots of multiplication, exponentiation, maybe factorials in our series representation, because then when I look at one term divided by another term, a lot of that multiplication, exponentiation, factorial stuff might all cancel away, making it really simple for us to then go ahead and evaluate the limit. I mean, if you can't evaluate the limit, then you can't use the ratio test, right? So anytime I see lots of multiplication, exponentiation, and factorials, that says to me the ratio test might be a good candidate right there. The root test is going to, so before I really go and look at this, the root test is going to be phrased identically to the ratio test. It's just that the limit that we're going to take is different. So this highlighted thing in gray right here, it's the literal only thing that changes when we go to look at the root test. So I want you to kind of see the big picture on this and not get trapped in the details for 1 second. See that the structure of these tests are identical. Here, we are going to take the nth root and let n go off to infinity of the absolute value of the general term in the series right there. And once again, If we end up with a result that's less than 1, we get absolute convergence, greater than 1 or infinity, divergence, equal to 1, inconclusive. So the structure of this test is identical. It's just this expression that we're taking the limit of is going to is a little bit different than we had in the ratio test right there. Again, we know that this absolute convergence means that it is convergent. Again, we know that this is kind of just telling us, right, that there's no info. You need to try a different test out there. It doesn't tell us convergence or divergence right there. Hopefully, it's relatively obvious to you that if you see a whole bunch of powers of n in your series description, then this is a great place to use the root test because nth roots will play very nicely with nth powers, right? So obviously taking nth roots is something that can get really hairy, especially in a limit type scenario. So I would avoid the root test unless I saw the powers of n hanging out there, right? So let's look at a bunch more examples now that we have these two more tests, the ratio test and the root test. And so I do want to say right now, technically today I'd say is a little bit more 11.6 than 11.7, but 11.7 is just strategies for testing series. So for our remaining examples that we're going to look at here, it's not like we're only going to look at the ratio and root test. I want you to sort of expand your mind and really what I think that you should be doing, especially for these last ones, now that you've seen so many of these, is you should absolutely be pausing this video at each one of these tests and attempting to prove the convergence or divergence on your own, and then seeing what I did with it. And remember, there's lots of different ways that we could come at these. We should certainly all end up at the exact same results, as long as that result isn't inconclusive, because that means try something else, but you should be trying these on your own here. So we're going to get some of these are going to be ratio root test candidates, but some of these are not for our remaining examples here. And then also remember, we have our super weird one to look at the end with our conditional convergence. So first example here, determine whether the following series converges or diverges. So this first one right here, the things that I'm seeing are, it's not in perfect form for the alternating series test because I don't have, a -1 to the n right here. It's really close. But the thing that I'm seeing that's more important to me is I have exponentiation and I have factorials. So I'm going to say here, combo of exponentiation and factorials says to me that's lots of multiplication going on. And lots of multiplication says to me we should use the ratio test because that's going to cause lots of things hopefully to cancel so I can evaluate that limit. And I'm going to try and write ratio so it's actually readable. All right. So let's scroll back up and remember the ratio test here. The ratio test says if you take the limit as n goes to infinity of the absolute value of consecutive terms of the series, if it is less than 1, then we are absolutely convergent and therefore convergent. If it is greater than 1, we're divergent. If it's equal to 1, we're inconclusive. So let's go ahead and set that up. So in our case right here, we want to consider the limit as n goes to infinity of the absolute value of a sub n plus 1 over a sub n. Right? For us here, this is the limit as n goes to infinity of. Now, you're always going to get, well, not always, but very common, you're going to get some big old bulky complex fractions here that you're going to need to manage. So it looks like I'm going to get a -10 to the n plus 1 over n plus 1 factorial, all divided by -10 to the n over n factorial. Right? So this is a great situation for us to do our keep change flip, rewrite this as a single fraction. And this is now going to look to me like I think I'm going to get a -10 to the n plus 1 times n factorial. That n factorial down here has flipped its way up to the top. Our denominator down here is going to be -10 to the n times the n plus 1 factorial. That's not a parenthesis, it's an absolute value bar. So do our little bit of algebraic simplification. So notice this is exactly the reason why we chose the ratio test is because we were anticipating getting nice cancellation. When I saw all of the exponentiation and factorial, that said to me, man, if I divided one of these terms by another, we'd cancel off so much stuff because it's all defined multiplicatively. So that division is going to help us do a lot of cancellation. So I think I'm going to get here limit as n goes to infinity. Why is it so easy for me to write this limit now and not with that when b's are involved? I don't know what's going on with that. So it looks like what we're getting here is a single copy of negative 10 survived on top. On the bottom, n factorial is all the first terms up to n. And bottom, it also multiplied by n plus 1, but all the previous n terms got canceled off by this guy. So this is literally just an n plus 1 on the bottom right there, which is clearly equal to limit as n goes to infinity of 10 over n plus 1, which is hopefully very obvious to you going to 0 in this case right here, a constant over an n. And so, therefore, the series is absolutely convergent by the ratio test. And therefore convergent. All right, so remember that the ratio and root tests give us absolute convergence, which is even stronger than regular old convergence. So since we get that it's absolutely convergent, we automatically get that it is convergent. We saw that theorem up above right there. So again, when you're seeing things that involve lots of versions of multiplication, remember multiplication isn't just multiplication. Multiplication is represented by exponentiation and by factorials as well. So all three of those things, multiplication, exponentiation, factorials, all three of those together give me good indicators to use the ratio test because I think I'll see lots of cancellation when I try to take the limit of the ratio of consecutive terms, right? So here's our next series to consider here. Negative 1 to the n plus 1 over the fourth root of n. So I'm guessing that at least a handful of you out there see that root and think, oh, maybe the root test. But remember, the root test is going to say to us, let's take an nth root. We already have a root in there. Taking roots of roots, I don't necessarily think is going to be the helpful thing for me to do. The root test is good when we have nth powers to cancel them out with the nth roots instead, right? So what I'm thinking here is this is not necessarily going to be a good candidate for that root test out there. I don't see lots of multiplication, exponentiation, factorials, so this is not necessarily a good candidate for the ratio test either, I don't think. And so what I'm thinking to myself here is this looks like it's in the form of an alternating series test. So let me kind of say my thoughts up here real quick. And actually, I'm thinking in my head right now, I think if you go hit this thing with the root test or the ratio test, I'm pretty sure you get inconclusive for both. I'm trying to do the mental math right now, and I think we get a limit as n goes to infinity of n plus 1 over n, and that's going to be 1. And so I think that those are going to give us our inconclusive result. All right, so this is in the form of an alternating series. So let's try the AST. Remember, the alternating series test says if the terms, if the absolute value of the terms essentially is decreasing over time, and if the limit of the terms, the magnitude of terms goes to 0, then we are convergent. So I'm thinking to myself that this series is really, can be written as what? Negative 1 to the n plus 1 times what? N to the negative 1/4 or something like that. That's going to be my b sub n right there. And so my question here is it going to be the case that our first check here, do we get that b sub n plus 1 is less than or equal to b sub n? In that case right there, I guess all I'm really seeing here is 1 over the 4th root of n plus 1. Is that less than or equal to 1 over the 4th root of n? You should actually notice real quickly right here, this is not just a generally true statement here. If you're taking roots of numbers that are between 0 and 1, you're actually going to get them to be larger instead of be smaller. But it looks like over here, I'm taking the root of a larger number than this one over here. And so as long as our n's are all of our positive integers, it does seem like our denominator here is larger, so the overall fraction is smaller. So this is true for all of our n's greater than or equal to 1 right there. Our second statement right here is we need it to be the case. Let's see if I can write it correctly. Limit as n goes to infinity of b sub n. We need it to be equal to 0. Our limit as n goes to infinity of 1 over the 4th root of n. Hopefully it's pretty obvious to you it's going to 0 there because the bottom is getting infinitely large. And so by the AST, it looks like this guy does converge. And remember, the AST did not give us any absolute value or any absolute convergence stuff. It just gave us regular old convergence, but that's sort of what we've been hunting for this whole time anyway. Our next series looks a bit like one that we actually saw in the previous video, but I kind of want to see like how we kind of like take our walk through all of our tests in association with this, right? So my first thought, it looks like it's an alternating series. So let's try the alternating series test. In this case right here, it looks like our b sub n is n over 5 plus n. I want to ask myself, is it the case that b sub n plus 1 is less than okay. Pen just had to take a little break right there. Less than or equal to b sub n. In this case, we're asking then is n plus 1 over 6 plus n, is that going to be less than or equal to n over 5 plus n? That is, let's see, not directly obvious to me. By the way, this is our first check right there. I guess we could try plugging in some numbers, and I mean, I always want to try it starting with the very first one. If I plug in n equals 1, is that going to be true? Here we'd get 2/7 is less than 1/6. That is going to be, wait, is 2/7 less than 1/6? I don't know if that's true right there. I'm going to put a question mark, because the other thing I'm realizing is that I'm going to have to take the limit as n goes to infinity of our b sub n right here and see what we get. And when I take this limit as n goes to infinity of the b sub n's, you should notice we're getting this to be equal to 1, which is not equal to 0. So it seems like the alternating series test has failed here. Now remember that the alternating series test doesn't say you either converge or diverge. It says you converge if you meet these two requirements. We don't know what happens if we don't meet these two requirements. So it looks like in this case the AST failed in the sense that we got no information from the AST. All right. So the point is, and I think that this inequality right there is not true, but I'm not 100% sure, but I don't care because there's two checks that need to be true. So I just saw if this one was easier to show failed, and so I just kind of moved on to that one. So it seems like the AST didn't work out for us. So the next thing I'm thinking here is, I don't know. I mean, let's just try some other things that we've got. What's up with our ratio test? Ratio test seems like it could work. And so the ratio test wants us to take the limit as n goes to infinity of the absolute value of a sub n plus 1 over a sub n. And that is going to be the limit as n goes to infinity of what? We're going to get n plus 1 over n plus 6 all over n over 5 plus n. And that's really going to be the limit as n goes to infinity of what? N plus 1, n plus 5 over n times n plus 6. Well, this is just a quadratic over a quadratic. You should notice that this is equal to 1. And so it looks like we're getting no info from the ratio test. All right. So two failed attempts so far, right? So we tried the alternating series test, we tried the ratio test right there. That didn't work. My next thought on this is we could try the root test, maybe, but there's no powers involved. All right, so I don't think taking an nth root is going to be super helpful for me because I don't have any nth powers for those to cancel away with. We're running out of things to try here. Is it a p series? No. Not 1 over n to the p. Is it geometric? No, we can't write this as ar to the n minus 1. Can we do the integral test? Integral test for this guy? No, I'm remembering that the integral test requires all positive terms, and we have some positives and some negatives here. So what else do we have left? I mean, holy cow. It's not a geometric series? Now here's one that I'm seeing, the test for divergence. That one we haven't tried. We tried integral test. We checked if it was a p-series. We tried. We don't have anything to really compare this to necessarily there. For the comparison test, alternating series test. Oh wait, the comparison test. Sorry, it requires all positive terms anyway, so we couldn't have done that. But this test for divergence seems like a plausible thing for us. If the series is convergent, then the limit of the terms should go to 0. If the limit of the individual terms doesn't exist or is not equal to 0, then it diverges. So let's come down and take a look at this guy down here. Well, maybe we can actually take a look at this guy right here because I'm noticing that uh, that I think I can take this limit right here. Now, we should notice that this test for divergence does not say, oh, b sub n is the positive part or take an absolute value. So we got to keep the whole thing right here. So it seems like our limit as n goes to infinity of our negative 1 to the n plus 1 times n over n plus, what were we looking at right here? N over 5 plus n over n plus 5. Well, what is this eventually going to look like right here? Well, you should notice that what's going to happen, so separate these two parts in your mind. What this part right here is going to do is just make us be positive, negative, alternating back and forth. This n over n plus 5, what is that eventually going to look like as n gets infinitely large? Just think about n over n plus 5. Well, that's going to eventually be 1. All right, the limit as n goes to infinity of n over n plus 5 is 1. That positive negative business that we've got going on out there means that our series eventually looks like negative 1, positive 1, negative 1, positive 1, negative 1, positive 1. So the limit does not exist by oscillation. Thus, the series diverges by the divergence test. Right? We see that the terms in our series weren't getting infinitely small, eventually making no contribution. They were just oscillating back and forth between 1 and negative 1 forever once they get very large. So it doesn't seem like the value of that series is ever settling down to something. It's just bouncing back and forth. It's essentially getting too big or too smaller, too big or too smaller, because we've got the difference between that 1 and that negative 1. Okay, it's getting one bigger, one smaller, whatever. But the point is, it's never settling down. The eventual contribution is always changed by 1 every term. And that means that it's not converging on some known value out there. So you should have all of these tests in your, available to you. We're trying them in the most sensible order. I think that this is the smart way to go through this thing is what we just did right here. AST is absolutely what I would think to try first because I see it's an alternating series. Then I think I can do some algebra. I'm pretty good at algebra, so the ratio test is good. Root test didn't even seem reasonable because nth powers aren't going to be reasonable to be taken right here. Or sorry, nth roots. P-series geometric, it's not of those forms. Integral comparison test didn't meet the requirements. Test for divergence was really the only thing we had left, and it turned out that that did actually work for us right there. So recognize that it might be the case that you need to just, run your finger all the way down your page on the list of tests that I'm sure that you've all set up for yourselves by now, to say to yourself, which of these tests should I be hitting it with? And you might need to literally try everything. I can agree that I often forget the test for divergence, even though it's our very first test that we got and one of our simplest ones. I usually forget about that guy, so it ends up being the last thing I use often, which shouldn't necessarily be the case, but it is. So let's go ahead and take a look at our next series here. So it's 1 over 2 times n to the a factorial of 2n. And so I want to remind you that factorial implies lots of multiplication, which is usually good for the ratio test. Because I think I'll get to see a lot of cancellation top to bottom when I take the ratio of 2 consecutive terms. So I'm thinking here, this is my a sub n right here. So I want to take a look at the limit as n goes to infinity of the absolute value of a sub n plus 1 over a sub n. I'm recognizing here that we're only going to get all positive terms right here, so I don't even need these absolute values. So this just looks like the limit as n goes to infinity of 1 over 2n plus 1 factorial all over 1 over 2n factorial. And if I'm going to try and work with this here, it seems like this 2n factorial on bottom is going to flip up to the top. On bottom, what do we really have? This looks like it's actually 2n plus 2 factorial. So it seems like if I'm going to try and kind of write this guy out, I want the cancellation to happen. The whole reason we're setting up the ratio test is to cancel some terms to verify that we're getting some desired result. And what I'm seeing is that it looks like this is the limit as n goes to infinity. I'm going to expand one of the factorials a little bit. I know that if we're looking at 2n plus 2 factorial, that's like saying multiply 2n plus 2 times 2n plus 1 times 2n times 2n minus 1 all the way down to 1, right? So this is my way of expanding what's on the bottom, is that 2n factorial, maybe I'll even put that in an additional parenthesis right there, is that I've picked off essentially the top 2 terms from that larger factorial on bottom. And what I'm seeing here now is it seems like that and that are going to go ahead and cancel, which just gives me the limit as n goes to infinity of 1 over a quadratic, right? And hopefully it is obvious to you that that limit therefore is then going to 0. So this is good. Remember, I'm going to scroll all the way back up. Remember that our ratio test said if we took that limit of the two consecutive terms in absolute value and got a number less than 1, then it's absolutely convergent. We just got 0, so that's great. So it looks like we are absolutely convergent right here. And so by the ratio test, the series is absolutely convergent and therefore converges. All right. Cool. I think we just got what, two more examples, and then I'm just, so we're gonna do two more examples, and then I'm gonna show you the super weirdness that happens with with conditional convergence. So our next guy right here, I am seeing two things. One, I'm seeing that this is clearly an alternating series, but I'm also seeing that there's powers of n on every term. So this is an alternating series. But I also see nth powers on every term. So that says to me, let's check out the root test. Take the limit as n goes to infinity of the nth root of the absolute value of a sub n. That's going to be the limit as n goes to infinity of the nth root of, now notice that this absolute value in here is essentially just going to discard our negative 1 to the n power. And it looks like, well, all we're getting here is limit as n goes to infinity of just the, so the nth root is canceling with the nth power, and it's just leaving us with 1 over the natural log of n. Since the denominator is getting infinitely large and the numerator is staying at 1, this limit is converging to 0. And remember that the ratio test and the root test have all of the same conclusions associated with them. So we got 0 just like we got in the previous problem. And so I think I can conclude here by the root test. All right. So again, if you see all nth powers, that's your good indicator for the root test. Root test is kind of really nice. I feel like I have rarely used it, but it's one of those things where it's like you look at a problem, it's like, everything has an nth power. Yeah, I'm going root test. And I pretty much don't use it in any other context. So it's sort of only useful in certain contexts, but it's pretty obvious when it is useful because you're going to take the nth root and just essentially discard all those nth powers out there. So I think this one's one of the more obvious ones. I feel like it's things like the test for divergence. It's like, well, I don't know what I'm supposed to use. That comparison test, I don't know what I'm supposed to use that or what I'm supposed to compare to. I get that some of these are other ones are a little bit weirder to use. I think that the root test is one of the most obvious ones that's out there. If you see all nth powers, use the root test. And it might be inconclusive and you got to try something else, but like that's always my like kind of go-to whenever I see those nth powers out there. So we got one more example that I want to look at, and that's because there is another way that our tests or that our series could be phrased that should indicate something to us. But since I know that all of you are not as widely experienced with recursively defined functions, it might not be as obvious to you what we should be doing in this case. So here is a series, but it's not written in series form right here. I'm just given the recursive definition. So what the series is the series a sub n. The series is the sum of the a sub n's. Right? But it's defined in this way right here. So the point is that we don't have an explicit formula to write down what the nth term is going to be. I need to know what the previous term is to know what the next term is going to be. It seems to be required to be defined recursively right here. So this is kind of a tough one because you don't have a formula for a sub n. However, the thing that I am seeing here is I would ask this: what is the ratio, or what is the relationship between a sub n plus 1 and a sub n? You do multiplication to get from one to the next. So since I know a relationship between a sub n and a sub n plus 1, and that relationship is multiplicative, what does that tell you? What test should we be looking at here? I am thinking about the ratio test. We want to take a look at the limit as n goes to infinity of the absolute value of a sub n plus 1 over a sub n. And this one's kind of funny. Watch how funny this one works out. You should notice that we only even have a definition for one of those two terms. I know what a sub n plus 1 is. It's 2 plus cosine of n over root n times a sub n. That's my a sub n plus 1. What's a sub n? Well, it's just a sub n. That was easy. Also notice our absolute value bars are doing nothing for us. Cosine of n can technically be negative, but 2 plus cosine of n reaches a minimum value of positive 1. So it's never negative. Bottom is always positive also. So absolute value bars aren't doing anything for us. So it looks like this is just the limit as n goes to infinity of 2 plus cosine of n over square root of n. And again, you should notice that that numerator reaches a maximum value of 3 and a minimum value of 1, while the denominator is getting infinitely large, and therefore this limit is equal to 0. This clearly converges by the ratio test. All right, so seeing these recursively defined formulas here can be a little bit weird to work with for exactly the reason that I stated right there. If you don't know an explicit formula for a sub n, most of our tests depend on that, but some of our tests don't depend on knowing a sub n, but being able to understand what the relationship would be between a sub n and a sub n plus 1. And we did have that based on the recursive definition right there. So that did give us access to the ratio and the root tests, and it was relatively obvious that the ratio test was better just because I never saw any powers of n cropping up out there. All right. So I think that's the last example I wanted to do. Now I just want to show you one. And this is one where you should just look at this and say, what the hell's going on here? And you're going to have to pay attention a little bit to some rearranging of some terms right here, but this won't be too difficult to follow, and we're going to arrive at an insane conclusion here, all right? So watch this. This is pretty cool. This is, I like to heavily discourage students from ever thinking that there's any tricks to math or that there's any magic going on. This is like as close as we ever get right here. So what's so weird about conditionally convergent series? Series that do converge, but not when you take their absolute value. We know that the harmonic series diverges, but the alternating converges, right? So the harmonic series, just the sum of 1 over n, diverges, but the alternating harmonic, the negative 1 to the n plus 1 times 1 over n, this guy diverges. This guy converges. We've shown both of these. We've proven both of those statements right there. That means that the alternating harmonic is an example of a conditionally convergent series. It's probably like it's the easiest one that I know how to like talk about, and so let's play around with it and see what happens. So here's what we've got. All right, so I don't want to like I want you to like kind of look at the same line as I'm looking at all the time here. All right, so here's what I've got. Here is the alternating harmonic series. We've got a term that gives us the alternating, a term that gives us the harmonic, right? We can tell because n plus 1 is the power that when we start with our first term being the n equals 1 index, when n is 1, we get an even power, so we get a positive first term. So we're getting 1 over 1, negative 1 over 2, positive 1 over 3, negative 1 over 4, positive 1 over 5, right? And what we know is it converges, and therefore it's reasonable for us to say that it's equal to some number. It's typical to just call that capital L right there. So I'm saying we don't know what the alternating harmonic actually converges to, but I know it converges, so let's just call its convergence value L. It's the thing that that series is going to be equal to if you added up all the infinite number of terms. So we're going to do some manipulation here now. So what we're going to do first is we're going to divide both sides of this equation by 2. On the right, that's really easy. We get L over 2. On the left, we're hopefully kind of obviously just getting the multiples of 2 in the denominator, right? 1, 2, 2 to 4, 3 to 6, 4 to 8, 5 to 10, 6 to 12. So I just divided all of these fractions by 2. They're all only half as big as they were before, so they all have twice the denominator size. All the signs stayed the same. You should notice that these just seem like a bunch of terms that crop up in the harmonic series, positives or negatives, right? Not worrying about that, but let's just throw in some zeros where those terms would be. I mean, when we divided this series by 2, we just got back a bunch more terms that seem like they already belonged in that series, right? These are just other harmonic terms that are out there, right? So all I'm going to do is throw into the slots where I feel like there's missing terms from the regular harmonic series. So that's where there should be the 1 over 1, but there wasn't one. Then we kept the 1/2. That's right there, positive 1/2. We missed the 1/3, so I put a 0 in to hold its slot right there. Next up was negative a fourth, and negative a fourth is my next thing. So this is me just slotting in some zeros of where I saw the odd denominators not appearing, right? Now what we're going to do is we're going to take this, the half of the alternating harmonic, and we're going to add it to the original alternating harmonic, right? So all I'm doing is setting up an addition problem right here. Oh, if you can't quit highlighting what I don't want you to highlight, Microsoft Word, I'm going to freak out. There we go. So all I'm doing here is saying, let's just do addition. So I'm adding together this equation on top and this equation on bottom to get this overall equation down here. So let's do the easy part first. On the right, when I add the value of the harmonic series to half the value of the harmonic series, I hopefully obviously get 3/2 the value of the harmonic series. Now let's see what terms we actually got back, right? So the reason I wanted to stick those zeros in there was to make sure that it was really easy for me to visually see what I was going to get when I did my math here, right? So 1 plus 0 is 1. Negative a half, positive a half is 0. A third and 0 is a third. Now notice here we got same signs, negative a fourth and negative a fourth. Well, that just gives me negative a half, right? Next up, a fifth and 0 gave me a fifth. Next up, we cancel negative a sixth and positive a sixth and get 0. Next up, a seventh and 0 gives us a seventh. Next up, we double up and we get negative 1/8. Negative 1/8 gave me negative 1/4. Next up, 1/9 and 0 is 1/9, etc., etc., etc. So now look at that sum that we see down here on the bottom and tell me what all denominators you see. I see a denominator of 1, of 2, of 3, of 4, of 5. I think I would get a 1/6 as my 2 terms away out here, a 1/7. There would be a 1/8 way out here, a 1/9. It seems like I'm getting back a bunch of terms I'm recognizing, but do they follow the right sign pattern? Positive 1, negative a half, positive a third, negative a fourth, positive a fifth. We're going to get a negative a sixth out there, positive a seventh, negative 1/8 way out there, positive 1/9. It seems like this is exactly the alternating harmonic. But the alternating harmonic, we already established, we said the alternating harmonic sums up to L. But this is equal to 3/2 of L. So it seems like we've concluded that L is equal to 3 halves L, which is obviously an impossible statement. There is no real number that satisfies that except for 0, and 0 is not what the alternating harmonic series is equal to. So this is really weird. And it gets weirder than that. This is just one weird example. It turns out, and this is crazy, and this is proven to be true, it turns out by rearranging the terms of any conditionally convergent series, you can get it to converge to literally any real number you want it to converge to. Literally every conditionally convergent series can be coerced, manipulated into looking like it is converging to literally any real number you would ever want it to converge to. That's crazy. So, this is sort of our conclusionary reminder now that we are wrapping up the first 2/3 of chapter 11 to remind you there is still a meaningful distinction between the idea of summing a finite number of terms where you can measure every one and see the final measurement, and summing an infinite number of terms where it seems like there's some screwiness going on way out there in the infinity of terms that's making something happen that disagrees with your basic intuition of how addition works. So it seems like our finite sum intuition has failed us in our attempt to understand infinite sums. And that's all we've been doing this whole time anyways, hoping that our understanding of how just regular old addition works between two finite numbers can be extended to apply also to an infinite number of numbers being added together. And what we've seen in this chapter is that mostly that's true, but it seems like these conditionally convergent series are ones where our intuition is now failing us about how we think about regular addition between two finite numbers versus an infinite series. That intuition does not seem to extend to our infinite series notions anymore once we end up looking at conditionally convergent series. So conditionally convergent series are crazy. And these are things where I hope that you can believe that in the year 2021, this is like math clickbait all day. Where I think it's the thing, I'm trying to remember right now. I feel like I should have just looked this up before I did this right here. I feel like there's a thing where I think, oh gosh, I'm gonna say a guess right now because I think I'm right, but I could totally be wrong about several facts about this sentence. But it's something like, I think that it's Ramanujan, very, very famous Indian mathematician, who I believe proved that, what was it, that the sum of alternating integers was equal to 1/12. So not alternating harmonic, that's 1 over the integers. I'm just saying straight up the integers, like 1 minus 2 plus 3 minus 4 plus 5. And that because that was what was it? Maybe that wasn't it. In any event, it's a series that clearly couldn't even be equal to a fraction at all, and he proves that it's equal to like 1/12 or something like that, and then later shows that it's like equal to like also 1 over pi or something like that, and like writes proofs that show that these are true. So this is just to say you should not trust conditionally convergent series. They can do very, very strange things to us, like converge to an infinite number of different values, which is unreasonably weird out there. And so this is just one of those things to say, just because you're really good at math and you're good at determining the convergence and divergence of lots of things now, this is maybe sort of one of those like conclusionary, humbling statements that says, well, I certainly don't understand it all the way. And that's an acceptable position to be in right here because conditionally convergent series just do really, really weird things right here. So remember to not trust your conditionally convergent series, but that we understand the distinction between convergence and absolute convergence out there as we've expressed here today. So kind of our takeaway from today is we've now produced this like giant list of tests that we might want to throw at series to determine whether that series converges or diverges. The reason why we're doing all of this here is because next week, our wrap-up sections of the semester is what we want to discuss our Taylor series. Taylor series are polynomial approximations of non-polynomial functions. And what we're going to see when we look at Taylor series is that sometimes when we form this infinite sum of polynomial terms, sometimes it actually just straight up converges to the non-polynomial thing that we were hoping it was going to be equal to. For example, we're going to find a Taylor series that is a polynomial that is an identical representation of functions like sine and cosine, and it will converge to the function sine and to the function cosine. That convergence matters. That says that Taylor series is straight up equal to the value of sine or the value of cosine at that current x value. On the other hand, we're going to see that there are some functions like the natural log function that even though I can build the infinite Taylor series that is supposed to be equivalent to the natural log function, we will be able to show that series never actually converges on the value of natural log, meaning if you're trying to estimate the function natural log with a polynomial, you will never be able to get it exactly correct by just introducing more and more and more polynomial terms. It will always only be a good approximation in a small neighborhood around the point of approximation, and it's always going to diverge away from the estimated function eventually. So the reason we're so interested in convergence and divergence is because our big goal of chapter 11 is to ask the question, could you build a polynomial with an infinite number of terms, whereby building the infinite number of terms, it eventually converges on being a non-polynomial function? And the answer is sometimes. We're always going to be able to build the series, but whether or not that series actually converges on the desired function or not is to be determined, right? That's the thing that we're going to want to actually look at out there in chapter section 1110 in particular. So as our wrap up to this class, we are going to look at Taylor series, polynomial series that are approximations of non-polynomial functions. And that's what we're going to wrap up this class with next week. We're going to wrap up this chapter 11 here. We're going to, again, kind of breeze through some things super quickly. Section 11.10 is our most important one, the final one, where we talk about Taylor and Maclaurin series out there. And I've got a nice big, just like you guys did your polar flows assignment, that was sort of like that specialty assignment I made for you guys. I've also made like a specialty assignment that's kind of similar in structure to that one that's associated with our Taylor series, where I'll have you guys as your kind of last homework assignment of the entire year. I'll have you prove Euler's formula. So our last thing to prove at the end of the semester here is in your final homework, you are going to prove that e to the I pi plus 1 is equal to 0. This is going to be your final conclusion on your final homework problem of the entire semester. I hope that that seems unbelievable to you, because that will make it all the more exciting when you prove it to be true. So I will see you guys for our last week of videos next week in week 15. Have a good one, everybody.